Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to continue a discussion on particle motion, so talk about position, velocity, and acceleration. And we're really going to hone down on the differences, or rather the relationships between the first derivative, the second derivative, and the original function. So we already know about those relationships from previous units when we're talking generally, but in terms of particle motion, we're going to talk about what derivatives mean in relation to the original function, when they're positive, when they're negative, when they're zero, undefined, all that good stuff. Okay, to start off, we're going to talk about average versus instantaneous velocity. This goes back to a question a unit or two ago where we were asked somebody's average velocity on the way to a store was less than the speed limit. So let's say the speed limit's 50 miles per hour. Their average velocity was 45, but somehow they got pulled over and were given a ticket. And the question was, well, how is that possible if the average velocity was less than the speed limit? And, well, the answer was it's possible that at a certain point in time, they were going faster than the speed limit, even though their average velocity was less. So average velocity, that's going to be found by taking the final position minus the initial. So we can say if P is our position function, P of B minus P of A all over the quantity B minus A. You could of course switch both the numerator around as well as the denominator. You just have to make sure you switch both. The instantaneous velocity is a little bit different, right? The instantaneous velocity is going to be found by finding the value or the slope of the tangent line at a specific point on the position function. So we could say it's equal to P prime at A, the derivative of the position function at A. All right, let's move on. We're now going to implement these two things in a problem. So I'd encourage you to pause the video, do these on your own. One is asking you to find the average velocity, one is asking you to find the instantaneous velocity. You are allowed to use a calculator here, and make sure you round or truncate to 3 decimal places. All right, so average velocity, we already know that's going to be the difference in the final position and the initial. So P of 3 minus P of 1 all over the quantity 3 minus 1. That is equal to average velocity. If I substitute those in, I'm just going to do this all at one time in the calculator. This gives us approximately, let me change those signs, approximately 0.2. It's one of the worst 2s I've ever done. All right, let's just do this all one more time. 0.274 if I'm rounding. Oh, it does give us units here. I was looking for those. Centimeters per second, because we're talking about velocity. So centimeters per second. So that's the average velocity on the interval t equals 1 to 3. Now the instantaneous velocity, you're going to actually go ahead and find the derivative here. If you're allowed to use a calculator, well, you could just use our tool on the calculator to evaluate a derivative at a certain point, so you wouldn't have to go through this all by hand. If you forgot about that though, P prime of t is going to be equal to e of t times sine of t. Derivative of e to the power of t is just e to the power of t, plus e to the t cosine of t. Then you could go ahead and punch that in for t is equal to 1.5. And that is going to give us approximately 4.787 centimeters per second. So you can see that at this point, the instantaneous velocity is much larger than the average velocity. So we have to know what's going on elsewhere. Maybe the particle is stopped, maybe the velocity is negative at other times, but at this at this point, the instantaneous velocity is 4.787 centimeters per second. All right, let's move on to average versus instantaneous acceleration. Going to be the same idea. The only difference is now we're working with the velocity function rather than the position function. So we have the quantity v of b minus v of a all over the quantity b minus a. That's for average acceleration. For instantaneous acceleration, we need to do the derivative of the velocity at a. So we would say v prime of a, or you could say, a of a for acceleration function, but v prime is telling you that it's the derivative of velocity. All right, same idea. Go ahead, pause the video, find the average and instantaneous acceleration for both of these questions. Same function, you'll notice, and same exact intervals. All right, so I just put everything up here for us because there was quite a bit to write out. We'd already found the v of t function, so you could just go ahead and use that from the first page. And once we apply the average acceleration formula, we get negative 10.403 centimeters per second squared. Those are the units for acceleration. For v prime of t, which is equal to a of t, the acceleration function, that just becomes long and drawn out. It's not a hard derivative to find, it's just lengthy. It does simplify to 2e to the power of t times cosine of t, and when I substitute in 1.5 for t, we get 0.634 centimeters squared per second. Really encourage you to become proficient in understanding how to use a calculator to evaluate a derivative. If you're allowed to use a calculator, it can just save you a lot of time rather than having to write out the derivative by hand and then substituting in to each individual t in your equation. All right, let's keep moving on. All right, so let's make sure we understand which functions of position, acceleration, and position, velocity, acceleration. So the original function f of x, that's always going to correspond with position. F prime of x, right? We've already talked about this, but that's going to correspond with velocity. And f double prime of x corresponds with acceleration. So that helps us know which function we're talking about. And again, if we're given one, we can go back and forth and talk about things about the other functions, even if we don't have the exact function for them. Okay, so it says, let's summarize the relationship between velocity and position. Use a graph below to help you visualize. Note that there may be more than one thing you can write down in the position column. So basically, we have these things about velocity, and we have to talk about what does that mean about the position. So if we're talking about, let's actually skip the first one. Let's talk about when v is greater than 0. So when our velocity is positive, that means the position of the particle is increasing. Or we could say moving, the particle is moving to the right or up. Those are the two positive directions. When the velocity is less than 0, right, we could say the particle's position is decreasing, or the position function is decreasing. And that means the particle is moving to the left or down. Those are the two negative directions. So when the particle is the particle's velocity is 0 or undefined, two things could be happening. One, the particle's position could be stationary. The particle could be stationary. Or the particle could be about to change directions. Could be about to change direction. And we will talk about how we can know the difference between those a little bit later. When the velocity changes from positive to negative, well, the position of the particle, or the position function, changes from increasing to decreasing. Just like we would say for a regular function, right? If the derivative goes from positive to negative, there's a maximum, and the derivative, or the original function changes from increasing to decreasing. You could also think about it as the particle stops moving to the right and starts moving to the left, or stops moving up and starts moving down. And just the opposite for changing from negative to positive. The position function changes from decreasing to increasing. So the particle, is moving to the left and then it starts moving to the right, or it's moving down and then it starts moving up. Okay, so we just have to think of these things in the real world context that they're in. So sometimes, when we say increase and decrease, and we have to think about what that means in terms of movement, right? Well, if the position function is increasing, the particle is moving in the positive direction, or it's moving to the right or up. And, if it's decreasing, it's moving to the left, or it's moving down, or in the negative direction. Okay, let's talk now about acceleration and velocity. So now we're looking at what the second derivative tells us about the first derivative. So again, we'll go in the same order. When the acceleration is positive or greater than 0, the velocity is increasing. Right? When a derivative is positive, the original function is increasing. Or in this case, when the second derivative is positive, the first derivative is increasing. When the second derivative is negative, the first derivative is decreasing. This doesn't tell us whether the velocity is positive or negative, right? Because I could be going forward, but slowing down because my because my acceleration is negative. Or I could be going forward and speeding up because my because my acceleration is positive. So just because we know if the acceleration is positive or negative, it does not tell us whether the velocity is positive or negative. We just know whether the velocity is increasing or decreasing. Now, when the acceleration is 0, that just means our velocity is constant. So velocity would be the same value. It's not changing at all. When the acceleration changes from positive to negative, well, when the derivative changes from positive to negative, our original function changes from increasing to decreasing. And when our acceleration changes from negative to positive, what have we not used yet? Maroon. Our velocity changes from decreasing to increasing. So that's going to do it for part 1 of this lesson. We will be back for a part 2 where we talk about some more relationships as well as go through 1 or 2 problems. So enjoy the rest of your day, or at least the time until you turn on the next video, and I look forward to seeing you next time.